Large language models are highly capable reasoning engines, but out of the box, they exist in isolation from your specific reality. Every model is trained on a massive but finite dataset. Once that training ends, the model hits a knowledge cutoff date. If a user asks about a proprietary internal document or a live flight status, the model has no access to the answer. Left with a gap in its logic, it hallucinates, inventing facts to fill the void. When organizations realize their AI lacks internal data, the immediate instinct is to attempt to teach it through fine-tuning. But treating a language model like a database is a structural mistake. Fine-tuning means altering the neural weights of the model itself. It is a computationally exorbitant process. Updating those weights to reflect new information takes weeks of processing, making it difficult to scale for enterprise data that changes by the hour. Furthermore, baking sensitive company data directly into the model's weights exposes that proprietary information to privacy risks. Once the data is part of the model's weights, controlling who gets to see it becomes an engineering nightmare. Injecting dynamic data into a permanent memory structure is an engineering dead end. To bridge the gap safely, we need a different architectural approach. The solution is a methodology known as Retrieval-Augmented Generation, or RAG. RAG utilizes the LLM as a real-time processing engine, rather than relying on its internal weights to store facts. Instead of relying on memorization, RAG gives the model an open-book exam. When a user submits a prompt, the system intercepts it, searches a verified external database, and hands the AI the exact documents it needs to read before it attempts to generate an answer. By separating the reasoning engine from the data storage, RAG achieves high accuracy and absolute data privacy without a single cycle of model retraining. We build RAG through two parallel systems. The ingestion pipeline prepares raw enterprise data. Immediately, we hit a bottleneck. Language models have strict context windows and cannot ingest massive databases at once. Raw data must be systematically sliced into smaller payloads. We call this data chunking. Engineers choose their slicing method carefully. A fixed size chunking strategy chops text every 500 words. It's fast, but it routinely cuts sentences in half, destroying the meaning. Semantic chunking, by contrast, is computationally heavier. It scans the text and only splits the data when it detects a shift in topic. Precise chunking is the bedrock of the entire architecture. If you slice the data poorly here, you guarantee the retrieval of broken or irrelevant context later in the pipeline. But computers cannot process strings of English text. To search through these document chunks, the system must translate human language into mathematics. We pass the text through an embedding model. This translator converts our text chunks into multidimensional numerical arrays, known as vector embeddings. These embeddings require a specialized storage layer, a vector database, built to hold and map these exact mathematical coordinates. In a traditional SQL database, searching for heart attack only looks for those exact letters. It fails to pull a document labeled cardiac arrest. Vector databases solve this through semantic search. The model evaluates medical meaning, assigning similar mathematical coordinates to conceptually related terms. Converting text into spatial math allows the enterprise architecture to retrieve data based on actual human intent, bypassing the strict limitations of exact keyword matching. Now that the data is structured, we activate the second half of the architecture, the retrieval pipeline. A user submits a query. The raw query pushes through the embedding model, translating the question into a coordinate within the vector database. The system identifies the nearest semantic neighbors in the vector space and extracts those specific chunks. This pulled data becomes our context. Next is augmentation. The system stitches the retrieved context and the original user query together into a single massive payload. Finally, we reach generation. The LLM processes this augmented prompt, now fully equipped with the precise proprietary data required to answer accurately. By injecting verified context at generation, the architecture grounds the LLM in specific facts, significantly reducing the probability of hallucinations. Standard RAG works for basic knowledge retrieval, but pure semantic search fails when queried for exact identifiers, like a specific serial number or employee ID. Meaning-based math cannot handle hard exact digits. To fix this, enterprise systems deploy hybrid RAG. This architecture fuses vector-based meaning with traditional exact keyword search to ensure no data is missed. We face a second structural limitation. Standard RAG treats all data chunks as isolated islands, losing the broader relational context between different documents. If the data lives in a complex domain, like legal compliance or deep research, we upgrade to GraphRag. GraphRag solves the isolation problem by explicitly structuring data as interconnected nodes and edges, mapping how different entities relate across massive databases. Mapping relationships mathematically ensures the system can trace complex dependencies that pure vector proximity would miss. The ultimate edge case is the multi-hop query. Imagine asking the system to compare the 2025 gold price hike against other metals and explain the macroeconomic cause. Standard pipelines break here. A single retrieval pass cannot pull pricing data, historical comparisons, and macroeconomic theory all at once. This requires Agentic RAG. This architecture grants the LLM the autonomy to evaluate a prompt and break it down into multiple sequential subtasks. Agentic RAG allows the model to utilize external tools, triggering API calls, performing live web searches, and executing iterative retrievals until it has enough synthesized data to answer the main prompt. It even includes self-reflective layers. The agent critiques its own drafted response, verifying the logic before outputting it to the user. RAG represents a modular engineering framework. By decoupling reasoning from memory, this system provides language models with a secure, verifiable path to enterprise utility.